Well, hello everyone and welcome. I know we are a small group today, but I understand the time frames that are happening at this point in time of the year. And so welcome anybody who's able to join us and follow along as we go. It's our last session for our math program for this year. And as promised, we said that we would leave algebra to talk about at this session, as well as statistics and patterns. So that's kind of going to be our day today. We are going to also have a chance to look at three videos that will tie into some of those and perhaps address some of the requests that some of you have been sending in about the Fibonacci series. Like, what does that mean? Not familiar with it. So we'll just go through a few pieces to go along with that as well and make sure that everybody feels comfortable before we're at the end of the session. So welcome aboard and let's get started. So I am going to go into our acknowledgement today. I've always throughout the series here put in a link at the bottom that deals with our Indigenous culture or relates to something that we're talking about in our unit. So today I am going to touch on that one because it ties very much into the patterning that we're going to do in some of the algebra. So we'll begin first with the acknowledgement. In the spirit of reconciliation, we want to acknowledge that this gathering is taking place on traditional lands across the province of Alberta, home to many diverse First Nations, Métis, and Inuit peoples. We acknowledge that this land is a traditional meeting ground, gives voice to its original peoples, and the story of creation of this country in a way that history has forgotten. And so I was looking for things that we could tie into those three particular organizing ideas that we wanted to finish today. And at the bottom here, you do have a link. There's more links in this. I just want to bring it forward to you. I'm sure many of you are already familiar with UCubed. It is a phenomenal site and a great site for math materials. But in this particular case, what we're looking at is we're trying to tie in some of the artwork that they have done into patterning. And so I just want to point out, we won't go into all of them, so we'll have time to watch some of the videos. There are some lesson plans that the speakers have shared with us, and they actually will get into your evaluating of algebraic expressions and also talk a little bit about the variables. But it ties directly into the pattern of the design that was created. So it's a very unique site. It's very nicely done. UCubed is not new to us, but the entire feature here is on Alberta Indigenous ladies who have shared materials with us. So take some time to go in there. There's a lot more in the artwork that links directly to the math outcomes, but I just wanted to highlight that one for you. Okay, so let's move on. So as I mentioned, the big rocks of today is algebra, patterns, and statistics. And as we're moving into that new curriculum of 456, patterns is a lot less about the patterns of shapes and more about the connection between algebra and the patterning. So we're going to try and build all of those together, and hence the order that we're going to cover them in as well. So we will go back over the order of operations. We've touched on it slightly, but I want to make sure that we're really clear about what is it that we do in grade 4 as far as the order of operations is concerned. And then we'll talk about equations. What do they look like in grade 4 and what don't they look like in grade 4? And the emphasis on preservation of equality. We'll talk about patterns, the square numbers, the triangular numbers. We'll look at increasing and decreasing, and then we'll investigate the Fibonacci series as well, the sequence. So we'll talk about that, and then we'll delineate the difference between arithmetic and geometric. A lot of you are familiar with those terms, but for some of you, that's a new one. It's a slide down from the other grades. And so we'll just cover that. It's not a difficult topic, and kids kind of like the titles that we give them. One being adding, one being subtracting or multiplying. So it's an interesting way for them to see something new. And we'll look at statistics, and we're going to really look at the verbs that are living in the world of statistics, because you're going to be adding in each of the grades 4, 5, and 6 as we move forward. But with statistics, we're actually engaging already in the grade 4. So what could that look like? And could I maybe tie that in with something other than just math? Could it be with my science curriculum as well? So let's begin first of all with algebra. So let's just look at, there's two cusp lines in algebra. And the first one talks about an expression can include multiple operations. So remember that an expression, the difference between the expression and the expression does not have an equal sign. An expression means I have a number of terms as we've defined already, but nonetheless, that's what we want to review today. And we have two different kinds of expressions that we can talk about. There's a numerical expression, all numbers, or an algebraic expression where I may have an unknown value. And that unknown value we'll talk about in 1.2. We're talking specifically in grade 4, the order of operations. We are looking at the 4 operations. So adding, subtracting, multiplying, and dividing. There are no brackets, so it's just the 4 operations. And when we look at the skills, we're looking at evaluating expressions according to the order of operations. In other words, students need to be familiar with the fact that there is actually a way that we solve them. We don't just randomly start from left and work our way to the right. And so in that case, when we're working on order of operations, we actually have to show students why there is an order. Why is it that we all have to follow the same thing? Because the answers could be very different otherwise. And we want consistency, we want an exact value, and we want that same value to be found wherever I live in the world. It doesn't matter. So we're going to look at how do I share that with students other than just telling you that we do multiplying and dividing first, and then we do adding and subtracting, which is true. How could I maybe show that to them? We don't want to model forever, but we do need to start there and make sure that they're understanding what it is actually that we're doing. Okay, and then when we talk about creating various expressions of the same number, in other words, in grade 1, we often say to them, how many ways can you show me 10? 9 and 1, 2 and 8, 4 and 6, right? Those are the same ideas. What are ways that I can show 2 expressions to be exactly the same value? We talk about the order of operations, the name order of operations. The title also implies that there is a specific order, and that order will grow from grade 4 to grade 5 and from grade 5 to grade 6. Some of the common misconceptions, and I know that's a little different than what we've done in the past, but this is a really good place to talk about misconceptions. Many of you, when you went to school, were taught an acronym that you could use when you were using the order of operations. It could have been BEDMIS, it could have been PEDMIS, and there's lots of different ones. Some use strings like words, and those are fine. It's not saying that there's anything wrong with that. There isn't. However, there are some misconceptions that come from that. So just being aware of that, it would be helpful. And those misconceptions really stem from the fact that some students believe that because you gave me the acronym BEDMIS and it's in a certain order, that is the only order that I do things in, that I don't necessarily do multiplying before dividing because that's what I see in the equation, in the expression. I do it because that's what it said in BEDMIS. And the answer is no, we don't do it that way, okay, or the other way around. So just being aware that sometimes students take those acronyms we give them and they memorize that to be the only routine. So we have to give them lots of examples where one would change the operation to come first. In the next one, it would be the other operation that comes first. So when we have a question like 2 plus 3 times 10, the answer is, does it equal 50? Or does it equal something else? And if it's something else, then how do we determine what that's going to be? And that's an important piece for our students to really understand and get. Okay, Rhonda, you can't hear me? Is there anybody else that cannot hear me? Or is everybody else okay so far? Just throw it in the chat box if I can just see or see a thumbs up that everybody can hear me. Okay, thank you. Rhonda, do you want to just check your sound again? and just see how it's going. Okay, so let's go back to our question. And that was whether the answer is 50 or not. And again, if I live on the other side of the world, anywhere in the province of Alberta, wherever we're watching this from, the answer should be the same. Doesn't matter where we are, because we're approaching it the same way. So again, we need students to understand that that order of the 4 operations starts with multiplication and division. And as we read a book, we're reading from left to right. And so if I encounter multiplication first, I would do that first. If I encounter division first, I would do that first. So it's whichever comes first from left to right. And once I've done the multiplication and or division, because maybe there's both, then I go back to adding and subtracting with the same idea. I'm reading from left to right. Do I hit adding first or do I see subtracting first? Whichever comes first is the one I'm going to do. But when I'm first teaching students that, it's fine just to put it on the board and just have them memorize that. But a lot of our students, as we've unpacked throughout the year, they're very visual and they need to see, what does this really mean? So color is a great tool when it comes to order of operations. That's a really important piece that we know, that we can show them what it is we're saying, that the order makes a difference. So here, when we go back to that question, 4 plus 3 times 5, that was my original question. So I could do it 2 ways. I could say that I have 4 plus 3, and that would be 7, and I'm going to multiply that answer by 5. In which case I would have 4 plus 3 down here, the dark color and the orange, and I have 5 rows of that. Or I have an array of 3 times 5, so 3 rows of 5 objects, which I have, and to that I added 4 individual pieces. And seeing those individual pieces sometimes makes it easier for students to understand why I have to figure out how much is in the group that's all together. And then I'm going to do these what we call add-ons on the end. So it's what's the bulk value. So if this is true, and I'm going to use that procedure that we talked about earlier, where I'm reading from left to right, and I'm working on multiplication and division first, then 4 plus has no bearing on what I'm going to start with. I'm focused on 3 times 5, which is this green array or blue array, whichever you want to call it. There's 15 in here, and to that I'm going to add 4. And we've already unpacked with them a number that how I add them, from what order I add, whether I have the 15 plus 4 or 4 plus 15, won't matter. That's going to be the same answer. So in this case, my answer would be 19, which is the correct answer. If I pay no attention to what order I do things in and just randomly go from left to right, whatever I hit first, then I would have had 5 rows of 7 objects, and none of them are necessarily the same. So I'm treating them as if they are, that the blues and the oranges were exactly the same items in the row, and they're not. They're separate, right? We've seen them. So in this case, I'm going to end up with an answer of 36, and that would be incorrect. And it should not be 35. Sorry, 7 times 5. There we go. So when we're looking at this, color is helpful. Cuisenaire rods are great, and we'll do that in just a second. So if your students have been working with Cuisenaire rods all year, they're going to be familiar with the rods. Let's bring them out and do them with order of operations as well. The other thing that I want to point out with the order of operations is that we typically, once we just start doing the algebraic part of it, and we go away from modeling, trying to get them to be a little bit more cognizant that when I'm working on my order and I do a step at a time, it's not necessary for me to try and do everything in one step. So typically what we try to do is have students recognize that there's kind of a V shape to my work. And that V shape at the very bottom of my V is my answer. And so if students can start to see that here was my original question, I'm seeing division first, so I'm going to do 4 divided by 2, and that gives me 2. That still leaves me with 2 times 3 plus 20. I have another multiplication before an addition or subtraction, so I'm going to do this part first. But in the steps that I'm doing one step at a time, working my way down, keeping in order the things I need to do from left to right, And at the very bottom, I should have my answer. So getting that V shape sort of in their minds and in their practice and routines is a great way for us to go back to and check each other's work to see where they're at. We know where we're doing kind of one step at a time. Students who are just learning order of operations love to try and do everything all at once in their heads. And of course, sometimes they forget. They forget that they've done something or they've done one number wrong and then we can't see it. So this kind of precludes that. If we start them off right, in grade 5, they would use the same thing because now we're going to add more to that order of operations. And then in grade 6, we add even more. So just sort of entrenching that inverted V or that V for them is a great way to do it. So how could I use Cuisenaire rods? Well, I could ask them to model a number. So I could say, can you show me what 10 would look like? Well, we know an orange rod is 10. We also know I could give you 2 5s. We also know that I could give you 2 groups of 3 and add a purple on the end. So here I see that these are 2 of the same thing. 2 of the same thing could be added together or more simply multiplied. 2 groups of light green or 2 groups of 3, so 2 times 3, and I add the purple, which is the 4. So again, they're starting to see that wherever I see multiplication or I see things that are the same color, that turns out to be a multiplication of that same value. And this is where color again helps. If you don't have Cuisenaire rods or you've got kids that don't particularly like them or you want a different approach, I could do it with a number line. I could do the same thing. I could say, could you show me what this would look like on a number line? Knowing I need to do the multiplication first, that means I have 3 groups, and they could use the jumps as well, whatever works for them. So 3 groups of 5. And to that, I'm going to add the length of 10. However, it's best for them to understand it's important that we start with the investigate and the explore first, rather than just putting the rule up on the board and saying, here it is, memorize this, let's go. Just so that they have an idea of what it is that I'm looking for and the fact that groups of things that look the same have to go together. So that means that I wouldn't take a green and add it to the purple because there's 2 greens. They're together as a group, they're together as a multiplication, and that in itself would tell me that I'm following an incorrect operation or rule. Okay, so you've got some examples there. Money, of course, is another one. We want them to keep working with money. Well, let's make sure that they use it as a tool. In this case, I want them to be able to see what's different. So in this case, it says, what is the numerical expression that expresses the value, right, of each of these examples below? Now notice that this is in cents and this is in dollars. You have to be a little strategic here because you don't want to mix and match. If you only want them just to treat them as different items, then you're going to have to say that it's 4 nickels and 2 pennies and name it as opposed to the value. But the question said, what's the value? So I'm dealing with pennies, I'm dealing with nickels, and that means that if I asked you to write an algebraic expression for this, I'll give you just a second to think about what you would write. And if you're a little faster, go ahead and do the bottom one as well, all in dollars. I know that these are each worth 5 cents, and I have 4 of them. So I could do a long repeated addition here, but that's not the idea. We've always said, let's try and be economical and efficient. So if I, instead of going 4 plus 4 plus 4 plus 4, or 1 plus 1 plus 1 plus 1, I can do that as a multiplication. In this case, I have 4 groups of 5 and 2 single ones. Could I have written that as 2 times 1 here? Sure, I could have, absolutely. But I'm just trying to show a little bit of variation here as well. So in this case, to figure out the value, I'm going to start with the nickels because there's my multiplication. 4 times 5 is 20, plus 2 more cents added on will give me an answer of 22 cents. What's my expression down here? In this case, I did both multiplication this time, so you can see both of them. These are all dollars, so I'm okay to keep going with the value of $1. That's what the number represents. So I have 4 times 1, and to that I'm going to add 3 times 2. So there's my expression. So I could work it out to be 4 plus 6, and they would do them as a V, one step at a time. And in this case, I'm going to end up with $10. So we can use money. Money's a great one because I can put dollars with dollars, and you can still use your paper bills. You can use all of them. And it also gets them to do their multiplication that they need to do. So just practicing doing it that way. Just be cognizant, though, that we're going to deal with cents with cents, dollars with dollars. And that means you could pull out your dimes, you can pull out your quarters, like all of them, right? It doesn't have to be just one. And that way the students get to see them in a different light as well. So let's look at 1.2, because that one is going to move away just from the straight order of operations. And what they're talking about here is writing an equation, right? An equation, remember, has an equal sign in it. So there's a little teacher note here, and I took this right off of the CPAR document, which will be posted for algebra very quickly here. In the teacher's note, we put in there a note that says there are 3 conditions, really, to have an equation. The most important of which is there has to be an equal sign. Didn't have that in an expression, right? There was no equals to something. There has to be an expression on the left-hand side and an expression on the right-hand side. And sometimes there's a little bit of confusion about that. The word expression, people think, well, that must be letters and numbers on both sides. And the answer is no. A number in itself is also an expression. So if I just say the number 4, is that an expression? Yes, it is. So when I say it has to have an expression on both sides, something as simple as 2 plus 3 equals 5 is an equation, which is true. The left side, when I add it together, does equal 5. 5 is equal to 5. I have an expression here, and I have an expression here. A single number can be an expression. So we would start first with simple numbers, just number equations. You know, give them a number 43, and how many different ones can they come up with in 15 seconds? You know, just say, I'm going to give you 15 seconds. What are ways that you can add 43 and have 43 on both sides? And I don't have to have just equals 43. I could have something like 40 plus 3 is equal to 38 plus 5, right? I could do that as well. It can be an expression of 2 additions. Could be a subtraction on the other side, right? Could be 45 minus 2. So just ways that they see that both sides are equal. So we're working on that balance scale. That's really where we're going to go here, is can they keep that balance scale from tipping one way or the other? And we do that by making sure both sides of the equation are equal. And that's what that preservation of equality that is stated in here is all about, is we're talking about keeping both sides of the same value. And in the end, as we move students forward into grade 5 and then into grade 6 and grade 5, we solve those equations. We're going to do that too, but we're going to do it not with variables. So here's an example where it says write an equation that represents the amount of money that's being shown. So I could write, I'm not saying this is the only way, but I could write, I've got 2, 4, 6, 8, 10. So I could go 10 times 2 is equal to 20. That's a perfectly legit equation, matches the value of what I'm seeing here. Here's my balance scale. And we might say to them, explain why this is considered to be an equation. If I understand that an equation must be balanced on both sides, same value on both sides, then a student should be able to say, I'm going to add 54 to 86, get my answer, and it should be the same answer over here when I go 4 times 35 if they're going to be balanced. And if those two numbers are not the same, then my conclusion would be, no, they're not. They're not equal. They're not balanced. So that's the kind of thing that we want them to be able to start with in grade 4. It isn't about writing equations with unknowns in it right away. There's a little bit of an investigation, and I took this one also from the CPAR document. There's quite a few in there, so this is a couple that we can just start with. But again, you've got money mats, and what we're trying to do here, this is the investigation. That's one of your verbs that you're supposed to do. Students investigate equality or the preservation. So I would need to try that. Would I do this with money? Sure, I would. I would give them the money and have them do it right in front of them. So on one side, they have a toonie and 2 loonies, and the other side, they have 4 $1, 4 loonies. And from over here, when I'm going through, I'm going to answer these questions. And the idea would be, when does the value change? If I take away a loonie on both sides, are they still balanced? Well, I have $3 then, I have $3 then. Yeah, they should still be balanced. Does it matter that one of them looks different? No, because the value is still 2 plus 1, which is 3. And that's what the question is the value the same? What if I put $5 into each one of them on both sides? Is it going to be balanced? And the answer would be yes. And so they sort of work through these. This is their investigation to work through so that they start to recognize when we say, to be balanced, I have to do the same thing to both sides to keep that balance from tipping. It's that rule that when eventually we start solving equations, you say what you do to one side of the equation, you do to the other. Why? Because I want to see that they stay balanced. That's why. So this is where we start. If you've got Cuisenaire rods, you can even do it with Cuisenaire rods. And if you've got the pan balances, remember the Cuisenaire rods are weighted. So you can put like an orange and 2 yellows to show that they're weighted. And then if I dropped a red one here and a red one there, they should still be balanced. And if I dropped a light green one on there, if I took something off, that's another way to show them that preservation of equality. That's a really easy one to do. Or better yet, set up stations in the classroom where they work their way around. And they have some that are Cuisenaire rods and some that are money, and maybe some that are pattern blocks. How do you make it equal? So if I have 2 green triangles, is that going to be the same as a blue parallelogram or rhombus? And the answer is yeah, absolutely. They just 2 of them versus 1. It's the same thing as a toonie versus 2 loonies. So just setting that kind of up experiment sort of across the room gives them that investigation that they're supposed to do. But it also really starts to solidify for them that it's not just the numbers on the board that we call the order of operations. And what does it mean to have that preservation of equality? So again, here's another example where I have an orange and a yellow, and I put a brown one up here. And what is it that I'm going to be able to do with that to find the missing one? So I could do lots of examples with them. So I'm going to just throw this into the chat box, the link again, if you can grab it from there. And we're just going to do just a couple of examples, just so you feel comfortable and good to go with all of these. Let me just grab our chat box. There we are. Okay, so it's in the chat box if you don't already have it saved on your computer. It's the same one we've been using all year. And I do like it simply because it doesn't have the numbers on it right away. And if I'm just working on preservation of equality, I really don't care that it has numbers on it. I'm just saying what balances to something else. So if we were going to pretend that we had a balance scale on here, I might say, let's grab a blue one. And remember that with the Cuisenaire rods, if they forget what these are and what the values are, that's fine, because I can take all of them and just slide them around until I get something that works for whatever the rule was that you're going to give me. So in this case, I'm saying, here's the blue on this side. And if the balance on the scale is on the other side here, what could you put over here that would balance that out? So go ahead and figure one out that works for you, or figure out 2 of them. So really what I'm doing is I'm looking for something that matches the length of a blue. The blue happens to be a 9, but that doesn't matter that I know it's a 9. So possibilities, lots of them, but I put a dark green and a light green. This is a 6 and a 3. So I know that these 2 are going to be the same. If I put them end to end, or if I want to double check, I can put them right on top of my blue, and I know that it's balanced because they're both exactly the same length. If I wanted to check if this one's going to work, I could slide it in on the bottom and say, oh, yep, there's another possibility. So again, you could say to them, find as many as you can, see if you can work with a partner at your table, see if you get more than they do, or just however. Remember also that when you're working with this particular site, that you have this, we hardly ever turned it on because we want the kids to think first before we just give them the answers. You can turn the grid on, like you saw in the example, just by clicking this, and then they actually see the grid lines in there. So if I really don't know any of these, I could say, well, I have this black one and I want to find something that balances it. I need it to be this many blocks long. I don't know that it's a 7, but I can count them. Or I just slide them over and match them. So that's one way to do the modeling of preservation of equality. And they really, really do need to understand that well so that it doesn't just become the sentence, what you do to one side, you do to the other. It has meaning to it. And that's where I'm getting to. Okay. The other piece with algebra would be even the questions that you see often on a PAT for any of you who've taught grade 6 at any time. So we often give them symbols, different symbols, and we say, what's the value of the symbols? So if I understand the preservation of equality, this mobile is only going to stay like this if this is weighted the same as whatever these two are. Because the number at the top told me it was 12, and this is sitting right in the middle of the bar to be balanced, I would know that half of it has to be sitting over here at 6. Now, could it be a different value? Sure, it could. There's lots of mobiles where you could come up with more than one possible combination. But in this case, I'm going to say, what if this is 6? If this is equal to 6, then these two also have to weigh out to 6, which would make each one of these 3 plus 3 to make them the same. So the purple would be 3, and the orange would be 6. But again, you need to look at different possibilities where they exist. They don't always. You'll have lots of opportunities to grab some of these. The CPAR document, we gave you a link. We've got a whole site of them. So if you have some children, and some of them love this kind of a challenge, there's some that are quite complex. It's definitely still within a grade 4 realm, but quite complex. They're not just simple, look at them, divide, and that's it. But I would have them write out what they did for an expression to show me how they got that value. Okay, so before I move forward into patterns, is there any questions? Anybody have any questions about algebra? Because I know this is a big one. Algebra has been lots of questions about it. So I just want to make sure that those of you who are here today, you had anything answered that you needed. So feel free to unmute yourself if you need to. Otherwise, we'll just keep going. Okay, let's look at patterns then. So when we look at patterns, I'm just going to make sure that we got a bit of a delay here happening. There we go. In patterns, we have some language in here that some people have emailed and said, when we do this session, could we touch on some of this? So we will. Today we will. We'll look at 2 videos. One of them will be the Fibonacci series. And you can show this one to students. This would be a great one for them. And now that it's springtime, this is a perfect time to bring out the Fibonacci sequence and to talk about it in terms of what's happening in the real world that I can see. That'll make more sense to you when we watch this if you're not sure of what I'm referring to. So we're talking about sequences of numbers, patterns of numbers, triangular numbers, square numbers. So we'll look at an example of those as well. And then we talk about how does that sort of pattern of examples of increasing numbers or decreasing numbers, most of the patterns the students will do will be increasing, but they can be decreasing. We'll look at how does this Fibonacci sequence fit into this conversation that we're about to have. So we want them to investigate increasing sequences, including the Fibonacci sequence, because it is an increasing one. There's a pattern to figure out what the next number will be. We'll show the students that. They wouldn't necessarily know that. But the power of the Fibonacci sequence isn't so much that they just know how to figure out what the numbers are in the sequence. It's the fact that everything they look at on a day-by-day basis, and most of us as adults don't necessarily think that way either. What we're looking at is actually that sequence of numbers in action. And that nature has used that sequence of numbers in its natural design of so many things. So we'll look at that as well in this video right away. And then we'll talk about how do they express a sequence of numbers. When we get into part 2, we're going to actually tease out the different kinds of sequences. So there's an arithmetic sequence and a geometric sequence. How I get from the first number to the second number to the third number is different in arithmetic than it would be in geometric. Not difficult for the kids to work through, but they need to be aware that there's language that's associated with each one. So that's the other piece we're going to unpack. We're going to watch this first one. The second one is music, and it reiterates through the music all the different diagrams of what the Fibonacci sequence is all about. But if I don't know what it is, then this won't mean anything to me. So you wanted to start with something with the students that's just give me an explanation. That's why I put down here that it's a simple explanation, gives them good examples. Then they're in a position in a few weeks to be able to go outside and find examples that they saw in the video.
Have you ever counted the number of petals on a flower? If you counted them on a flower with petals all intact, you would likely discover that the number of petals is a Fibonacci number, that is, a number from the Fibonacci sequence. Many flowers have 3, 5, 8, 13, or 21 petals, all of which are numbers in the sequence. The leaves of cacti and the seeds of sunflowers are arranged in both left and right-handed spirals. The numbers of seeds or leaves in these spirals are also generally in the Fibonacci sequence. We have 2 hands, both of which have 5 fingers, and each finger is divided into 3 parts. All of these numbers are also Fibonacci numbers. Moreover, the lengths of the bones in our hands also fit into Fibonacci ratios. So, what's the Fibonacci sequence anyway, and why is it seemingly everywhere? The Fibonacci sequence is a series of numbers in which a given number is the result of adding the 2 numbers before it. So, if you start with 0, the next number will be 1, followed by 1, followed by 2, followed by 3, and so on. As you can see, every number in this series or sequence is obtained by adding the 2 preceding numbers. Individual numbers in this sequence are often referred to as Fibonacci numbers. Mathematically, the Fibonacci sequence is represented by this formula, where n is greater than 1. You can use this expression to find any nth digit in the sequence. This fascinating sequence is widely associated with the mathematician Leonardo Pisano, also known as Fibonacci. He hailed from the Republic of Pisa, which is why he is also known as Leonardo of Pisa, and is considered to be one of the most talented mathematicians of the Middle Ages. At the time, Europeans were still using Roman numbers, while Hindu-Arabic mathematicians were using a different number system that was more robust and efficient. Fascinated by the brilliance of the Hindu-Arabic numeral system, Fibonacci brought it to the Western world in 1202 through his now famous book, Liber Abaci. In the book, he reviewed and compared the Hindu-Arabic numeral system with other systems, such as Roman numerals, and described how using the Hindu-Arabic system made calculations faster and easier. Although his book contains the earliest known description of the Fibonacci sequence outside of India, it was described in ancient Indian texts by mathematicians as early as the 6th century. So, what makes this Fibonacci sequence so special? To the uninitiated, this famous sequence may just seem like a series of numbers, but the Fibonacci sequence has been discovered and rediscovered in various forms, not only in mathematics, but also all across the natural world and in our everyday lives. There's also another exciting offshoot of the Fibonacci sequence, the golden ratio. Suppose you have 2 quantities, A and B, wherein A is greater than B. Now, add A and B and divide that sum by A. If this ratio comes out to be equal to the ratio of A and B, then you can say that A and B have a golden ratio, which is represented by the Greek letter phi. Write down the Fibonacci sequence on a piece of paper and calculate the ratio using this formula. You will notice that all Fibonacci numbers have the golden ratio, the value of which is close to 1.618033. In geometry, when the golden ratio is applied as a growth factor, you get a special type of logarithmic spiral, known as a golden spiral. Simply put, a golden spiral gets wider by a factor of phi for every quarter turn it makes. You can find examples and manifestations of the golden ratio and golden spirals in countless places in your everyday life. Seashells are some of the most common examples of the golden spiral found in nature, but ocean waves, hurricanes, flower buds, snail shells, and spider webs are just a few of the other naturally occurring examples. Many artists use the golden ratio or the golden spiral in their creative works. Legendary painter Salvador Dalí explicitly used the ratio in his masterpiece, The Sacrament of the Last Supper. Architects also commonly use the golden ratio when designing buildings and other massive structures. Popular Swiss-French architect Le Corbusier, who is widely acclaimed as one of the pioneers of modern architecture, explicitly used the golden ratio in his modular system. From snail shells, flowers, and bananas to the inside of the human ear, iconic buildings, and galaxies far out in the cosmos, the golden ratio can be seen everywhere. This is probably why it's also known as the divine proportion. There are so many places to find the golden ratio or Fibonacci numbers that it's impossible to list all of them in one place, and the list is ever growing. What other examples of the Fibonacci sequence or the golden ratio have you observed in your life? Tell us in the comments below.
Okay, now I know it sounds like that, wow, that's a lot of info, but really what the Fibonacci sequence is telling us is that we have the opportunities to use a ratio that exists, and it's being used and has been used for thousands of years, quite literally, because the Greeks built all their temples based around that rectangular proportion. We use that because it's pleasing to the eye. They have found that that 1.6 ratio is what we typically look around us on a day-by-day basis, and we see things that are satisfying to us, and they're satisfying because they're in an appropriate proportion. It's not all square, and all square does not give us that same satisfaction, and that's been proven over and over and over again. If we look at flowers, lots of our flowers have a pentagon shape, but they themselves have that same ratio of the sides if I were to put rectangles inside of it and start building it. So that's really what this is just showing them. There is another movie, another video called Donald Duck in Mathmagic Land. And some of you may have seen that as a student. Some of you might have already shown that to your students. If you haven't, you might want to use that one as well. It's 26 minutes long. It's a Disney cartoon the whole way through. It's old, it's not new, but it does an excellent job of showing all the different kinds of things that happen in math. And one of them is the sequence of numbers. There's a magic pencil that's writing the sequence of numbers down, and they start to talk about this magic proportion. But they also show it that if you play guitar, or you play the harp, or you play music, all of those are built on that same proportion that was being talked about. So when we look at this Fibonacci sequence, that's what it is. It's a series of numbers that end up giving us a proportion. If I had to summarize it for students, it's a series of numbers. I can predict what the numbers will be just because the pattern doesn't change, but they result in a ratio that gives us this, what we call the golden rectangle or the golden proportion. And it's a pleasing use that architecture has used over years and years and years. Snails use, as they show you. When you look at this video below, remember there's no explanation in there, but it provides you with lots of pictures to back up what they've said. Some of this is quite technical. The students are not going to use the formula, but they understand that it shows up all over the place. So when I went to Greece, for example, I've been there quite a few times, and we took students, and that was one of the very first things that they point out to you is where this golden rectangle exists in all of their buildings. And once you see it, once you start to connect it, you realize that when you look at your own homes, not every window in your home is a perfect square for a reason. Not only does it not look great when they're all perfect squares, it doesn't give you that same pleasing ratio of 1.6. And so you see that in a lot of the buildings that we have. You'll see that in pansies when you look at pansies. Again, this is kind of where the Fibonacci sequence goes to. So in the other part too, when we were talking about the triangular numbers and the square numbers, like what does that mean? It's a pattern, it's part of a pattern. So here I start with 1 dot. And when I go 2 by 2, I get 4 dots. And when I go 3 by 3, I get 9 dots. And when I go 4 by 4, I get 16. 5 by 5, I get 25. I might say to students, does anybody see a pattern? What do you think the next array might look like? So 6 by 6 is going to be 36. 7 by 7 is going to be 6. So this is what we call square numbers. What are they? You know them to be 1 squared, 2 squared, 3 squared. You know that because you've done exponents before. They haven't, and they won't do that until they get to grade 6. But they can see that I'm multiplying the same length, creating a square to find the area or the number of dots inside that array, always gives me a square. The other place to show them that square numbers exist is taking a multiplication table. And if I say, what is a 1 by 1? That gives me a square right here. What's a 2 by 2? There's another one. So I can also find the square numbers by just taking a different colored marker and doing the 5s, doing the 6s, doing the 7s, doing the 8s, so that they can see what those look like. And the value of the square is right here in the corner every time. So there's other ways that they can find square numbers. What about here? This one says, is this arithmetic or geometric? So let's take a step down into 1.2 where they said there's different kinds of sequences. One of them is called arithmetic. So arithmetic, and the easy way to teach students that is the A's go together. Arithmetic means I have a sequence of numbers, and to get from one number to the next, I added something. But then I'm adding exactly that same something to every number to find the next one. So that's what an arithmetic sequence is. A geometric would be multiplying. I started a number, I multiplied by something, and when I multiply, I got the second number, and I'm take the same number and multiply, I'm going to get the third number, and take the same number, I'm going to multiply and get the fourth number. So arithmetic means to add the same number. It's called the common difference from one term to the next. Whereas geometric means I'm finding a common ratio or common rate. I'm multiplying by the same number all the way through. So we have some examples down here. We have 0, 2, 4, 6, 8, 10. So you say to students, what do you think the next couple of numbers might be? Well, in this case, it would probably be 12, 14. How do I know that? Well, to get from 0 to 2, I couldn't have multiplied because 0 times anything is going to give me 0. So I added 2 to get to 2. Does it work? Let's check. If I add 2 again, will I get 4? Yes. If I add 2 again, will I get 6? Yes. So it's like skip counting by 2s. That's really what you're doing. What about over here? I've got 5. I went to 10. Well, I could be multiplying by 2, or I could be adding 5, right? There's always a bit of a debate in some of them. So the third term should help me decide that. I'm going to 15. Okay, well then that's not necessarily always going to be that I'm adding 5. In this case, if I multiplied by 2, I got 10. To get here, I'd have to multiply that number by 3. That's not a consistent number. So this is an arithmetic. I added 5, I added 5, I added 5, I added 5, and then I can keep going. I could say, can you find me the next 4 numbers by adding 5? What are they doing? They're skip counting by 5s. I could have them add 3s or 4s or 10s or 22s, like whatever you want that number to be. It doesn't matter. As long as they have an opportunity to figure out, can they determine whether or not I'm adding? Or let's look over here. Here's where I added 2. Here I went from 2 to 4. Well, maybe I'm still adding 2. Oh, then I jumped to 8. Well, that's not going to work. There's no way I can add 2 and get to 8. So go back again. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16, and so on. So this is an example of a geometric. This is an example of arithmetic, both of these on this side. They're both examples of increasing because the numbers consistently, continuously are increasing in value. Most of the ones that we're going to do with students are increasing. As they get into the older grades, we're much more adept to being able to give them equations where they can increase or decrease. We can give them decreasing ones. It doesn't mean that we couldn't do that. It does mean, though, that they would be maybe a finite stopping point. Is there a finite stopping point here? The answer is no, because for every number that I write down, there's going to be another number. There's going to be another number. That's what the 3 dots are also saying. It continues on forever. If I started with 17 and the next number was 14, probably implies that I'm subtracting 3. That's still arithmetic. I'm using the same number, the opposite of addition. In this case, I'm going to subtract 3, but at some point, it's going to stop because our students don't go into negatives. So that would be a decreasing pattern with a definite endpoint on it. So we see here that we've got the values. I can write them out as multiplication. Students could show us What is the equality, the equation that would give me this array? Same thing with any of the ones that are down here. So we have the answers at the bottom. And if I were to say, you know, what's the 10th number in each one of these that I just went through, the 10th number is down at the bottom. So you can jot it down and you can ask them that. And 10th number is not impossible for grade 4s. They can count by 2s or multiply by 2s. They'll figure that out. It's not a big problem for them. So there's some opportunities for them to try something out. We also had triangular numbers. So much like the squares, what do I see? I see that I started with 1. I increased the row. I have now got 2 rows, 1, and then the next row has 2. I now have 3 rows. I had 1, 2, and the next row has 3. So what's happening is for every row, I also increase a number, and that gives me a triangular array to it. I can also say, what is 1 plus 3? And the answer is 4. How do I get to this one? If I went 4 plus 6, I would get 10. So the previous numbers added together can give me what the new number is going to be here. These are examples of things that students could use, and they're scaffolded for them because it says, how many purple circles did you have in the first one? How many purple circles in the second? How many purple in the third, and so on. How many spoons? That's what's around the outside. How many spoons were there around the first one? 3. How many were there around the second one? 6. So then they can start to see what's the relationship between the number of dots and the number of spoons. And we can have that conversation of what kind of sequence it's going to build. So these examples exist. It's not imperative that they do every kind of example like this. They need to be able to identify, and they should be able to create. If you say to them, starting with the number 4, okay, that would be a great formative assessment. Starting with the number 4, can you make me an arithmetic sequence and a geometric sequence? And they could do whatever they want. They could say, I'm going to add 2, I'm going to add 3, I'm going to add 6, whatever. And they're going to create their sequence for arithmetic. They could say, I'm going to multiply by 10, but remember, they don't know all the multiplication skills beyond too far. So I could multiply by 10, by 3, by 4, it doesn't matter. But as long as I keep the same number and they can show me and talk to me about the same number, they have found a legitimate geometric series. So sequence. So then it's easy for you to just pick a number at random. Or I often say to students when I would do this with them, I would just have a grab bag. Whatever number you grab, and nobody gets the same number. That way they might talk to each other, but they can't copy off of each other. So you grab a number, whatever number you've got, show me an arithmetic sequence, show me a geometric sequence. Those are just great, simple little assessments that you could use here. I've also included a growing patterns. This is a bit of like a performance-based assessment that you could use, where they trial through some of these to see whether or not this pattern is growing or not. Again, it doesn't have to be an assessment. It could be just a group activity that they're working on, or in pairs, or in groups of 3, whatever. But this comes from the NCTM, and it's really well done. So it lays it out for them. It's not like they need a ton of support to go through it, but they would need to understand what's happening first about the sequences of numbers before we go there. Okay, is there any question on that? I'm not sure that any one of the 3 of you asked about the Fibonacci sequence, but is there anybody that needs any questions answered on that one? Okay, let's look at statistics then. So stats is it's kind of neat. It grows from grades 3, 4, 5 into what they're going to do, and each year we scaffold a little bit more into it. But by the time they get to grade 4, you already see the word engage. In other words, we want them to be able to frame a statistical question. We want them to carry out the statistical process, which means they can do the question. They're going to collect the data that hopefully helps to answer that question. They're going to represent the data that they've collected somehow in using one of 3 different kinds of graphs, or all 3, and then tell me why one would be better than the other. And then they're going to interpret their data. What can they conclude from what they've seen in the data that they've shown? That we had way more of this, or they were all about the same, or we didn't see the answers we expected, we saw this happen, whatever, okay, however that turns out. So could I do something like that with a science unit? Of course you could, because there's lots of places where they have to do investigations and they have to frame a question in their scientific method. So merge scientific method with my statistics and math, and I could do the same thing. But there is, just want to be sure that everybody's clear on statistical questions. We can ask all kinds of questions, but are they statistical questions? So we're going to watch, not the whole thing, we're just going to watch a little bit of this video at the bottom. I'm suggesting everybody
Hey guys, it's Kaylee. This
watch this
lesson
one.
is an introduction to statistics, where we'll cover statistical questions and dot plots. Let's get started. You've probably heard the word statistics or its abbreviation stats before. Statistics help us answer questions like, who has won the most times in your video game? Or how many times and how fast did I run on different days this week? Statistics is the science of collecting, organizing, analyzing, and interpreting data. In statistics, data is very, very important. But how do we collect data? There are a few ways. We can run an experiment or have a survey. But in both of these ways of collecting data, there is one main thing in common. We have to ask a question. When we ask a question to collect data, it needs to be a statistical question. A statistical question is one where you expect to get a variety or a lot of different answers. Which of these do you think is a statistical question? How tall are basketball players? What time did you wake up this morning? How much money do people typically spend on cars? Do you play soccer? Let's get started.
Oh, my apologies.
Main thing in common. Statistical question.
Sorry, guys.
Statistical question. How tall are basketball players?
I just wanted to pause it there for a minute. This is a good place to pause this video and just give them a chance to even talk amongst themselves. Which of these is a statistical question? Which one will give them a variety of answers? And that's the key piece, is that we want them to be able to discern before they start to do their own investigation, engage in an actual investigation of their own. They have to be able to come up with a good question. And a good sort of rule of thumb when it comes to statistics is have students write 2 or 3 questions down and then share them with a partner to see whether the partner agrees that there would be a variety of different answers. So of the ones that she's giving in an example, which ones do they believe to be statistical? Which ones do they believe are not? And what's the reason behind it? And then, of course, we can start the video and chat.
What time did you wake up this morning? How much money do people typically spend on cars? Do you play soccer? Right, it's these two here. But how do we know that those are the statistical questions? It's because when we ask them, they will provide us with a variety of different answers that we will use as data. Whereas these two here can only give us one answer. Be careful not to confuse statistical questions with survey questions. If we have a statistical question, how tall are basketball players? We will have to take a survey of many different basketball players and ask a survey question like, how tall are you? You can think of a statistical question as one where you would have to ask a lot of different people the same survey question to collect data. How much money do people typically spend on cars?
Oops.
Do you play soccer?
Oh, that video is not wanting to shut off today. So there's more to that. It will go through then, how do I create a dot plot? How do I do a bar graph, a pictograph? So it'll talk about representing the data. And I don't want to go through that right now, but what I do want to make sure is that our students are really clear on what a statistical question is, because that is really a key piece to the kinds of things that they have to do in order to engage in the process of gathering their statistics. So part one is really, what is the problem? What's the question? How am I going to frame it? Then in part two, they're going to actually use that question, or they should use that question to engage in all of these steps. And that's why I say having a variety of different option questions that they could go to would be helpful for them. So, and that's what part two is about. Now that you've got the question, you're going to go out and figure out who you're going to go ask and get the data that you need. Then you have to represent this. And in grade 4, the representation of a bar graph, a pictograph, and a dot plot has actually already been done in grade 3. Now, and in grade 2, actually. But because this is our new year with this, we're going to have to assume that they don't all know all of those. They're probably familiar with the bar graphs, depending on where they've come, at what point they've come into this. They may do the pictograph already. Dot plot might be new. It's not difficult. They know the bar graph. They know how to do that. But it might be new to them. So it's worth going through and just doing a quick review. And that's what's at the bottom here, are just reviews of bar graphs, dot plots, and this one's bar graph and pictographs. And the other thing with the pictograph, I want to just remind everybody that a pictograph has the same image when you make the graph. So if I talk about a concrete graph and I was comparing, you know, the different kinds of shoes that I see in a classroom, so I might see runners and I might see slip-ons and I might see sandals and I might see, I don't know, platform shoes, whatever. I have all these different possible shoes, and I might show a picture of each one of those, creating sort of my own concrete graph. Looks like a bar graph. But to become a pictograph, I have to come up with a picture, a generic picture of a shoe, and that shoe will represent each of the findings that I had for each of the other ones. And that's the difference between a concrete graph and a pictograph, is that we have to have the same. Because if they're not the same image, you're seeing strawberries here. If I don't see the same image, then I have no way to compare how these actually fit together. Or if I have half a strawberry, I don't really have a way to compare that to whatever's above it. So when they do a pictograph, we have to make sure that they are the same image that's being used all the way through. And again, when they justify their choice of a graph, and my first starting this off, I probably would have them do all 3 graphs. Some graphs give us more information quickly. Some graphs are more detailed. Some are easier to read given the question that I had. So having them do all 3 lets me have that conversation. And is it possible to have all 3 of them could have been a good choice and it wouldn't have mattered which one I chose? Yes, absolutely. But what they're also getting at here is, did you choose the right scale? So what if the maximum number I had of anything was 6? If I chose a scale that started at 0 and it was going up by 5s every time, so incrementing by 5s, that scale probably isn't going to be very helpful to me, because those numbers are just going to be compacted down so much. It's going to be hard to recognize what 6 looks like. I'll be doing a best estimate. That might be one where going up incrementally by 1s or maybe 2s might be the way to go. So that is the big piece in grade 4. I already know how to do the graphs from grade 3 and grade 2. I now know what a statistical question is. I'm going to go through and do my own investigation or exploration of my question, collect my data. I need to be able to show you I know how to find an appropriate scale for me to use to model that. And although this is not, okay, and I just want to reiterate, this is not something that they would be expected to do in grade 4. It's a great picture. And the reason I love showing this to students is we say that it went from 0 to 800. And what do you notice? Well, it's going up by 100 each time. And then over here, they have this little zigzag. And so we tell students, well, you know, sometimes when there's not much happening at the bottom, some people will put a zigzag in, meaning the numbers are actually there. It's just I'm condensing it down so I don't have to label a whole bunch of empty space. and I'm going to start at 350. But sometimes when we do that, although there's nothing wrong, they've not done anything incorrectly. If I put the zigzag in, I've done everything I need to do. If I'm a company and I'm trying to sell something, or I want to make something look better than maybe it is, here's what it looks like when it increments by 100. Here's what happens when I start down here at 350 and then start going up by 50s. It makes it look like, wow, look at the huge increase that happened. Now that's only because of scale. Are these points correct? Yes, they are. Is the graph drawn correctly? Yes, it is. But that's how sometimes when we get ads on TV, they make things look better, and it's the scale that's doing that. They're not being incorrect. They're not in any way doing something wrong. But what they are is they're making it look better than maybe it is. So it's just good for students to understand when we say picking a scale is important. This is an example of that. You can get most magazines that you find. You can go in and find graphs that have this kind of an issue in it, where they're trying to promote something, sell it. They make it look better than it did. And one of the common things that I tell students is, I'll give them an example. Years ago, there used to be a commercial on television about Advil. And they used to say the people in Orillia, Ontario, 80% of the people in Orillia, Ontario use Advil when they have a headache. And I thought, wow, that's an amazing number and a stat to put out there. Not incorrect, not wrong, not misrepresenting, but definitely inflating, because they only asked 10 people. So 10 people isn't a lot to say an entire city would be represented by that. Maybe I just happen to be standing in the place where people buy the Advil or whatever the case may be. So it was just an example that we're not doing anything wrong, but we can definitely use it to our advantage. So scale is an important thing for them to understand. This might be another one too, where you've got the choice of graph, comparing different graphs and interpreting the graph. That would be where I would have them do all three and then talk to me about it. Maybe that's the exit ticket. You can say, which one of the three do you think is the best graph for your question? Why? Okay, that's an exit ticket. That's a great assessment question right there. Okay, so that's kind of stats. And the only thing that they add in stats now from grades 5 into grade 6 is just more detail. They're going to add more into their investigation. They're going to look at bias. They're going to look at things like, am I using a scale differently? Could I use a scale differently? Could I use a graph to my advantage? So those are the kinds of things that will get unpacked. But this is kind of the foundation of it. So that's why it's important for them to understand those two big concepts of what's a good question, statistical question, and then what scale should I use on my representation that I'm doing. So that kind of overarches our 5 sessions of unpacking the organizing ideas that you have in grade 4 this year. I know it's been kind of a blitz. It's the first time through. It's everybody finding their way to go through it. But hopefully you've been getting enough information to at least feel that you've got some terminology, maybe some examples that you can use. Again, just a couple of things just to wrap it up for the year. You always get a survey question that's mailed to you and emailed to you. I know that surveys are not necessarily, but here we are talking about statistics. They do give us feedback. They do help us to do planning and what your needs are. So this is a good time for you to start thinking about what are your needs for next year? Like now that you've unpacked grade 4 math, what do you see as kind of next steps for you that would be most helpful? That's the kind of information that would be helpful to us as well, whether it's to us or to your local consortia, depending on where you are. That's the kind of information that's really helpful at this point. We know that we don't have any new curriculum coming in as far as the LA, that's all done. We've got math, that's all done. So you have science 4, 5, 6 for those of you who haven't started science yet. That's what's coming in fall. And so there will be sessions on that as well. But nonetheless, in math, just the first time through, now what? What is the next piece that would help you the most? So give that some thought. And remember too that the CPAR documents that are going to be found on the ARPDC site will be of great help to you in that they will give you examples, they will give you assessments, they will give you explanations, they'll give you additional websites. They'll also tell you which of the textbooks in your school, that's in your school right now, what page should I go on to find this information? And because you're grade 4, it might not come out of the grade 4 text. It might come out of grade 5. It might come out of the grade 6 text. So those pages would be outlined for you in those documents as well, as is Mathology, Math Up, all of those pieces. So you have these important links that we've been talking about all year, but this is your new Learn Alberta. Remember, that's where you get your curriculum documents, but you also get your boards. You're looking for resources. You're looking for any kind of information as far as what's been approved for in Mathology. You've got some resources there and gizmos. The ARPDC site is where we are posting all of this, like these sessions that we're doing, the CPAR documents, all of those will be there. We are starting to transition some of those CPAR documents into New Learn Alberta. If that's the site you prefer to go to, then that's where they'll be eventually, not all of them right away. But nonetheless, the ARPDC site is there for you for all of your course subjects. And then the math verbs, don't forget that those would be important to have throughout the year, because that's gives us that common language that we need to have. So that'll be an important piece as well. Okay. Okay, are there any questions? Rhonda, can we get the slide deck today? Oof. Okay, I did not download it. If you throw your email into the chat box, I'll grab it really quickly. As soon as we're done, I will send it to you. Absolutely. So anybody who would like it, just throw your email in and I will, Rhonda, I think I have yours anyway. I don't think you need to worry about that. But yes, I will get that out to you for sure. Okay, I'm going to stop the recording here just so that you don't feel like you have to ask a question on the